Most prospectors in California walk straight past one of the clearest signals of hidden diamond potential: sugary quartz veins that cut across serpentinized terrain. These veins often appear dull or chalky and are dismissed as unremarkable. But in the right geological context, they act as silent signposts pointing to diamond-hosting pipes. The opportunity is lost not because the quartz is rare. It's everywhere, but because its critical differences are ignored. If you don't know what to look for, you'll never know what you just missed. The key lies in recognizing that not all quartz is created equal. In diamond-favorable regions, quartz often forms through late-stage hydrothermal activity tied to deep mantle intrusions. The result isn't a gleaming crystal cluster. It's a weathered, granular mass with sugary texture, typically opaque white to light gray, sometimes with reddish iron staining. Unlike high-temperature quartz associated with gold or copper systems, this low-temperature quartz has a granular look and a brittle fracture pattern, often running perpendicular to fault lines or old shear zones. When it crosscuts ultramafic rock, especially serpentinite, a key surface indicator of deep mantle material, it deserves closer inspection. In California, most of these clues converge in specific tectonic blocks along the western Sierra foothills and parts of the Klamath Mountains, where old cratonic fragments and subducted slabs meet. While full kimberlite pipes haven't been commercially mined in the state, fragments, dikes, and weathered lamproite have surfaced in placer concentrates, often in drainages fed by quartz-bearing slopes. What's most often overlooked are the veins that appear too dead to warrant attention. But sugary quartz in the right setting frequently contains accessory minerals like chromite, ilmenite, and even occasional pyrope garnet, all indicators of diamond potential if confirmed by simple field tests. What makes this miss so costly is that sugary quartz doesn't demand expensive gear to identify. With a hand lens, you can often see the broken, granular texture that distinguishes it from the smooth cleavage faces of massive quartz. Light doesn't refract evenly. It scatters slightly due to microfractures and fine inclusions. If the surrounding rock is dark green to black with a slick, waxy surface and weak magnetic response, you may be looking at serpentinized peridotite, the kind that hosts kimberlite intrusions in other parts of the world. Add in a weakly magnetic sweep showing iron titanium minerals, and the case for further sampling strengthens. Yet few bother to sample these zones because the quartz doesn't look right. It lacks flash, color, and gemmy appeal. But what it does offer, when properly read, is a rare window into deep earth processes that can deliver diamonds to the surface. Most prospectors never dig past the surface signals. They move on, unaware that a tiny fracture vein in sugary quartz just intersected a long-weathered mantle-derived conduit. But what if you don't want to miss it next time? The next step is learning what visual and tactile differences separate promising quartz from junk. That's where most fail, at a glance. So how do you read quartz before you even break a sample? The answer lies in the light. Ordinary quartz reflects it with a clean, vitreous luster, almost glassy when fractured cleanly. But quartz associated with deep earth pipes and diamond indicator zones behaves differently. It scatters and mutes the light, giving off a greasy, waxy, or even matte appearance. This dullness is not a flaw, it's a flag. It often results from micro-inclusions, subtle weathering, or complex intergrowths with minerals like chromite or ilmenite, all of which compromise transparency but enhance its diagnostic value. In the field, the quickest read comes from a dry rub with a thumb. If the quartz feels sugary, gritty, like compressed salt rather than smooth glass, it merits closer inspection. This texture often correlates with recrystallized quartz under low-temperature, high-pressure regimes, especially in tectonic settings where serpentinized peridotite or altered basalt is nearby. That gritty feel doesn't just indicate weathering. It points to a specific thermal regime and, potentially, a deeper source. Another fast read is translucency. Hold a thin piece up to the sun. Barren quartz often transmits light clearly through the edges. But quartz near diamond-bearing zones may look cloudy, fogged, or blotchy due to internal fractures and foreign mineral inclusions. Under loupe magnification, you may even spot tiny metallic specks, possible chromite or ilmenite, especially near fracture intersections or around granular knots. These are your trigger points for sampling. Color matters too, but not in the way most expect. While pinks and purples from iron or radiation exposure draw the eye, they rarely correspond to diamond potential. Instead, it's the off-white, bone gray, or rusty-stained quartz in the right rock host that tells the real story. Reddish iron films on surface fractures often signal oxidized accessory minerals nearby. Another soft tell of heavy fraction minerals deeper down. Clean white quartz in granite can be worthless. Iron-streaked quartz in serpentinite deserves your attention. Field discrimination often fails because most rely too heavily on overall appearance. But by learning to isolate three variables, luster, texture, and translucency, you dramatically reduce false negatives. Each one is non-invasive, rapid, and free. These are clues you gather before you even break rock. And when more than one trait stacks up, sugary feel, dull luster, and weak light transmission, it becomes a smart candidate for testing. Still, visual signs alone won't close the case. You need terrain context to validate whether these quartz traits point to deeper potential or are just a weathering fluke. That's where the map shifts dramatically. Because in California, not all zones are equal. Certain regions are simply built to deliver diamonds. If you know where the ancient conduits run, not every quartz signal matters, unless it appears where the deep earth once ruptured. In California, the difference between barren and diamond-prospective zones is written not in the quartz itself, but in the rocks it cuts across. The richest clues appear where fragments of the Earth's mantle were shoved to the surface, especially along the periphery of California's ancient cratonic route. This isn't guesswork. It's plate tectonics, frozen in stone. Most of the state rides on younger, tectonically jumbled crust, terrains welded on during the last 200 million years. But along a narrow belt from the northwestern Klamath Mountains down through the Sierra Nevada foothills, you'll find slivers of something older, denser, and deeper. Ultramafic complexes like the Rattlesnake Creek and Feather River terrains. These are the broken, oxidized tops of once mantle rocks, mostly peridotite, altered into serpentine and magnetite-rich masses. This is where you watch quartz behavior closely. Here, sugary quartz isn't random, it's residual. Its cross-cutting pipes long since weathered, delivering subtle indicator trails where the host kimberlite has eroded away. The critical mineralogic pairing occurs where these ultramafic belts intersect fault zones, especially zones that once served as conduits for ascending mantle-derived magma. Quartz that fills fractures in these contexts may seal off pathways carved by ancient kimberlitic or lamproitic pulses. Even when the pipe itself is long gone, the pressure regimes that formed it leave behind indirect signs. Clusters of heavy minerals, magnetic disturbances, and telltale vein textures that distinguish them from hydrothermal or tectonic quartz farther afield. These terrains are rare and patchy, but accessible. In the north, the Trinity Ultramafic Complex exposes large swaths of serpentinized peridotite, with historic reports of chromite and garnet in the surrounding drainages. Farther south, near Placerville and Mariposa, long-neglected shear zones run through serpentinite and host sugary quartz veins that once puzzled gold-focused miners. They looked for free gold and ignored the heavy concentrates that sank too deep in the pan. Today, those concentrates are being re-examined for ilmenite, chromite, and pyrope garnet, the silent trail of deep mantle intrusions. Terrain context does more than point you toward likely ground. It protects you from chasing ghosts. Quartz veining in granitic terrains or sedimentary host rock, no matter how sugary or mineral-rich, rarely links to diamond-bearing sources. The chemistry is wrong. The pressure history doesn't fit. But when sugary quartz appears in or near serpentinized ultramafic zones, especially where fractures align with known faulting, the odds shift sharply. The answer lies in the rubble. Specifically, the rubble moved by machines, not by hand. Throughout the 20th century, multiple road cuts, reservoir clearings, and dam excavations across California's interior highlands exposed strange, blue-gray decomposed rock with embedded quartz chunks, heavy and fine-grained. This material was dumped, bulldozed, or buried during construction. Engineers thought nothing of it. Geologists labeled it as altered basalt or metamorphosed sediment. But to the trained eye, some of that rubble bore the hallmarks of weathered kimberlite, long since mistaken for mundane debris due to the misleading presence of sugary quartz and the absence of visible diamonds. The critical misread came from quartz's camouflage effect. In several locations, such as the spillway cuts near the Oroville region and certain Caltrans slope reinforcements near Weaverville, rock samples containing ilmenite and garnet were discarded because the surrounding quartz veins were chalky and non-reflective. They didn't resemble the vivid hydrothermal quartz of known gold zones. Without gold color or gemmy sparkle, the rock was ignored, even though it held key accessory minerals tied to diamond pipes. This problem repeated in the dredge tailings of Central Valley foothill rivers. In the early 1900s, bucket dredges and later suction systems churned through gravels that included serpentinized rock and sugary quartz clusters. Concentrates heavy in magnetite and ilmenite were recorded, but dismissed as non-economic by operators focused solely on visible gold. The same concentrates, had they been reprocessed with a sieve and thermal tester, would have flagged pyrope garnets, chromite grains, and potential microdiamond traces. What fooled even experienced surveyors was the close resemblance between quartz found in metamorphosed volcanic terrain and the sugary quartz linked to deep source intrusions. Without context, without knowing the host rock history, this quartz told no obvious story. It required someone to notice that the quartz sat in decomposed rock with a greenish-blue hue, high in magnesium, with fine disseminated iron-titanium flecks. Most never looked past the quartz, and so they missed the pipe fragments. Today, some of these historical dump sites remain partially exposed, weathering back into creeks or being used for road fill. In a few confirmed cases, reanalysis of rock from these old construction zones has revealed mineral chemistry consistent with kimberlitic or lamproitic origins, environments that can transport diamonds from the mantle to the surface. The quartz never carried the diamonds itself, but its presence, fractured and veined through decomposing ultramafics, served as the only visible surface signal of what lay beneath. The pattern is now clear. Where sugary quartz appears with heavy mineral residue in altered ultramafic rubble, it may not be quartz you're chasing, it's what came up beside it. So how do you begin identifying those key indicator minerals on your own? In the field, without a lab? You start with a loupe, a magnet, and your pan, and you stop thinking about quartz as the goal. Instead, treat it as a signpost. When sugary quartz appears in or near altered ultramafic terrain, your next move is to look beneath it, inside it, and around it for the true payload, indicator minerals. These include pyrope garnet, ilmenite, chromite, and magnetite. Unlike quartz, these don't shine or fracture the same way, but their density, color, and magnetic response tell a story few field hunters bother to hear. First, focus on loose material near the base of quartz veins. Erosion over time will concentrate the heavier minerals downslope or in adjacent drainages. Using a standard hand pan, concentrate the fines from stream sediment or slope wash near sugary quartz exposures. After washing down the lighter material, look closely at what settles in the back corner of the pan. Heavy black or reddish-brown grains that resist movement in swirling water may be your first sign. At this point, dry your concentrate and pass a small rare earth magnet over it. Magnetite will jump instantly. Ilmenite may respond weakly or not at all depending on its iron content. Either way, separation by magnet gives you a usable fraction for close inspection. Under a 10x or 20x loop, pyrope garnets typically appear as deep purplish-red rounded grains. They don't fracture like glass, they look water-worn, even when freshly crushed. Chromite, on the other hand, appears black and submetallic, often with a slightly pitted or granular surface. Both are denser than quartz and will sit at the bottom edge of your pan after repeated passes. But this step requires more than observation. It demands judgment. Pyrope garnets by themselves are not proof. They can appear in metamorphic rocks unrelated to diamonds. What matters is their association. If pyrope appears alongside ilmenite and chromite, especially in terrain with serpentinized peridotite and sugary quartz, the probability curve bends sharply in your favor. There's also a tactile check. Weight in hand. A single rounded grain of ilmenite or chromite will feel heavier than a similarly sized piece of quartz. Over time, this becomes intuitive. Combine it with color recognition and magnet response, and you've just built the first layer of a field-based indicator suite. No assay required. These minerals hide in plain sight, often scattered invisibly through creeks or stuck to the bottoms of quartz boulders. Most prospectors never collect or test them because they don't glitter or look gemmy, but they are the geological fingerprints of diamond-bearing magma conduits. If your quartz vein yields even one of these under magnification, it's no longer just a rock, it's a lead. Now that you've located potential indicators, the question becomes, how do you trap them consistently, cleanly, and in a way that preserves sample integrity for testing or resale? The next step involves more than a pan. It requires a method. This is where many eager field hunters stall. They spot heavy grains, maybe even isolate a few garnets or black specks, but without repeatable process, their finds are unprovable and unmarketable. What separates luck from evidence is consistent concentration. That's why the simplest breakthrough after visual ID is upgrading your pan technique to a sieve and sluice system tailored for heavy minerals, not gold. Start by dry screening bulk material using standard mesh sizes. A number 20 mesh, 0.85 mm, filters out the bulky gravel, while a number 40 mesh, 0.425 mm, begins isolating the grain sizes where indicator minerals concentrate. Diamond indicators are typically finer than visible gold, and often sink too quickly during rough panning to be noticed. Running your quartz-adjacent sediment through a dry sieve first gives you a focused, manageable fraction. Next, use a modified gravity separation method. If water is available, a battiste-style pan or mini-sluice with a catch mat works best. Unlike traditional gold sluices with riffles optimized for flake gold, you want shallow vortex traps or vortex matting that holds dense sands and spherical grains like garnet or chromite. Run your pre-sieved material slowly and in small batches. Observe what holds back, especially the darkest and most spherical grains. Collect these into a concentrate vial labeled with GPS coordinates, host rock notes, and depth if applicable. If water isn't available, use a plastic tub to replicate gentle pan action. The key isn't speed, it's finesse. Heavy minerals can be lost with a single rough swirl. Instead, fill the pan with just enough water to suspend the fines, tilt to allow slow rolling, and let the densest grains settle into the lowest corner. Use a snuffer bottle or tweezers to extract specific grains for closer inspection. Field concentration isn't just about getting samples, it's about grid repeatability. For every promising sugary quartz site, take at least 3 samples. One directly beneath the quartz, one 2 meters downslope, and one from the nearest drainage or depression. This lets you triangulate whether indicators are truly sourced from the quartz vein zone or washed in from elsewhere. If the same suite appears in multiple spots, You're likely near the erosion zone of a deeper intrusive body. After drying your concentrates, reapply the magnet sweep. Then, under a loupe, sort by color, luster, and grain shape. Ilmenite often appears dull metallic gray to black, heavier than it looks. Chromite is black and submetallic, often with granular texture. Garnets, especially pyrope, may range from deep wine red to reddish brown. If all three are present in a single sample run from sugary quartz terrain, you've just hit a field-positive cluster, worthy of full documentation and next-level testing. False positives can stall or derail a field campaign, especially when the concentrate looks promising but delivers no value. One of the most deceptive culprits? Quartz itself, masquerading as a host or halo when it's merely tectonic filler. Field workers frequently misinterpret its presence, especially when sugary texture, color zoning, or vein clustering mimics known indicator settings. But without verifying its context, those promising signs become distractions. To break the illusion, you need to read quartz habits, not just appearance. The first step is identifying the type of quartz deposit: tectonic, hydrothermal, or magmatic. Quartz formed from tectonic compression, common in shear zones, often appears as thin, tightly folded veins running parallel to foliation. These veins are usually barren. Their sugary texture comes from pressure dissolution, not mineral-rich fluids. If your sugary quartz appears tightly folded or stretched along metamorphic banding, it's a warning. This is likely recycled silica, not part of a deep source conduit. In contrast, quartz tied to diamond-favorable magmas tends to fracture the host rock. It cuts across foliation, not with it. These veins may appear chaotic, with angular edges or infilled breccia textures. The sugary consistency here is secondary. It forms when hydrothermal fluids cool rapidly within fractured ultramafic zones. These are the types of veins worth following. Cross-cutting geometry always ranks higher than aligned or conformable quartz when evaluating for mantle-derived indicators. Next, examine host rock response. In promising zones, the quartz is hosted by altered peridotite or serpentinite, rocks with high magnesium and iron content. These host rocks often display a greenish-black sheen or slick-inside surfaces. A weak magnet will respond to magnetite traces. When sugary quartz crosscuts this type of rock and produces visible fracture halos with accessory minerals, the chance of deep system origin rises. In barren zones, quartz usually appears in more neutral lithologies: schist, phyllite, granite, or volcaniclastic units. It may still form sugary veins, but without the associated heavy minerals. Even if a pan shows black sands, they often consist of simple magnetite or hematite without ilmenite or chromite. These areas can fool beginners. The weight in hand might feel right. The look might be close. But a single magnet sweep followed by loupe inspection can prevent wasted effort. Another key signal: the absence of reaction. If your quartz veins show no alteration halo, no staining, no embedded accessory grains, and no heavy fraction in downstream pan samples, they're likely non-prospective. Real indicator-bearing zones are messy, chemically and texturally. The quartz isn't clean. It's mineral-stained, fractured, and often hosts ghost grains of denser material in cavities or fracture lines. One final check: test a fresh break. Use a rock hammer to split a sample. If the fracture is smooth, conchoidal, and glassy with clear translucency, it likely formed in a high-temperature or low-pressure setting, not compatible with deep-source magma. But if the break is granular, blocky, and mutes light, even internally, you're still in the game. Few disappointments hit harder than isolating a vivid red garnet or a sparkling black crystal, only to discover it has nothing to do with diamonds. The field is rife with imposters, and unless you know their tricks, they'll waste your time and skew your grid. The most common offenders? Zircon, spinel, and high aluminum garnet. All can appear in heavy concentrates. All can look convincing under a loupe. And all can lead you miles off track if you don't verify with simple, targeted tests. Let's start with zircon. It often presents as small, high-luster crystals, colorless to yellow, brown, or even reddish. Under a loupe, zircon may exhibit strong sparkle, sometimes mistaken for microdiamond reflections. But it's usually too small and too light to sink alongside true indicator minerals. A key giveaway is its tendency to show rounded edges and fracture faces under magnification. Most importantly, zircon has a much lower density than chromite or ilmenite, around 4.6 g/cm superscript 3 versus 4.7 to 5.2 g/cm superscript 3, and lacks magnetic response. If a suspect grain shows sparkle, but doesn't sink as quickly in the pan or reacts weakly to gravity separation, it's likely zircon. The surest field test? Drop it into water on a precision scale or test tube rig. It'll float longer and displace less water than a same-size ilmenite or pyrope. Spinel adds another layer of confusion. Black, submetallic, and dense, it mimics chromite visually and often forms in similar geological contexts, but it rarely occurs with pyrope garnet and typically lacks the titanium content that flags true kimberlite derivation. Magnet response is a key separator. Chromite and ilmenite often show weak to moderate magnetic response due to iron-titanium content, while spinel remains mostly inert. Also, spinel has a lower luster, more like a dull coal than polished metal. If you're unsure, crush a grain gently with pliers. Spinel often powders cleanly, while chromite fractures irregularly. Then there's garnet. Not all garnet is pyrope, and not all red garnets point to diamonds. Many field hunters mistake almandine garnet, common in metamorphic schists and gneisses, for pyrope. The colors can be nearly identical, but density and inclusions offer a way out. Pyrope garnets are higher in magnesium and tend to be glassy, round, and deeply colored without visible inclusions. Almandine, by contrast, often contains internal flaws or silvery platelets. Their source rock is also revealing. If you're finding garnets in quartz veins hosted in mica-rich schist or granitic pegmatite, you're likely holding almandine. Pyrope prefers ultramafic hosts. One powerful, low-cost field test here is specific gravity via water displacement. Place the cleaned grain on a milligram scale, record dry weight, then suspend it in water on a fine thread or slide. Record the submerged weight. The formula, dry weight divided by dry weight, wet weight, gives specific gravity. Pyrope should fall between 3.7 to 4.2. Almandine ranges lower, typically 3.5 to 3.9. It's a subtle difference, but enough to split real indicators from red herring garnets. You may also encounter high-density glassy fragments, especially in placer zones, that mimic small diamonds. These high-index simulants, like cubic zirconia, sometimes wash down from human activity or industrial runoff. They may even fool a thermal probe, but they will always fail under one test: the loop check for double refraction. Moissanite and similar fakes often show facet doubling under magnification, whereas diamonds do not. This is why no single test should ever carry your interpretation. Build a suite: visual, magnetic, specific gravity, and loop-based optical checks. With practice, you'll start eliminating false positives in under a minute per grain. The breakthrough rarely comes in a blaze of glitter. It creeps in with a pattern. That's exactly what happened in a dry Central Valley drainage, where a solo prospector logged sugary quartz boulders in a gully west of the Sierra foothills. The surrounding terrain was a tangle of oxidized serpentinite and peridotite fragments, long dismissed as non-productive by gold hunters. But instead of chasing visible metals, he focused on what settled below those quartz boulders after each winter rain: a dense black, magnet-reactive fraction that resisted every pan swirl. At first, it looked like magnetite, but a closer inspection, magnet sweep, loop magnification, and SG testing revealed a repeating suite: rounded black grains, chromite, submetallic silver flakes, ilmenite, and several blood-red garnets with no visible inclusions. The quartz, brittle and dull with sugary texture, was dismissed by earlier searchers as metamorphic filler. Yet this prospector had the missing piece: terrain context. The drainage cut directly across a decomposing lamproite dike, a rare, mantle-derived rock type similar to kimberlite and capable of carrying diamonds. The lamproite had weathered to clay-rich rubble decades ago, masked by flood silt and vegetation. The sugary quartz, cross-cutting it, held the only visible surface expression. The red garnets were small but sharp. SG testing placed them near 4.0. The chromite showed weak magnetic response, and ilmenite grains sank quickly in water despite their small size. 3 samples from different grid points all returned the same indicator suite. Realizing the importance of repeatability, he returned 2 weeks later with a systematic plan. Sieved 5-gallon buckets at number 20 and number 40 mesh, water displacement rigs for in-field SG checks, and bagged concentrates from each quadrant of a 10 by 10 meter grid. Over 30 samples were processed. A full 18 showed at least 2 valid diamond indicator minerals. 5 showed all 3, pyrope, ilmenite, and chromite, plus sugary quartz and decomposing lamproite fragments. It was no longer coincidence. It was a pattern. He sent 10 grams of heavy concentrate to a regional lab, marking the bag garnet/ilmenite sweet, serpentinite overlay, lamproite suspected. 2 weeks later, the lab confirmed the presence of mantle-derived ilmenite, Fatio3, CR-rich chromite, and G10 pyrope garnet, a subcategory specifically tied to diamond stability zones. No macrodiamonds were recovered, but 3 microdiamonds under 0.2 millimeters were detected using caustic fusion. What made the find so compelling wasn't the size, it was the trail: a misread terrain, a dismissed quartz texture, and a few overlooked black specks had masked a diamond-bearing system for decades. And all of it had been exposed during natural erosion and ignored by generations of gold-centric prospectors. But the bigger shock came later, when he compared his GPS logs to old soil anomaly maps from a 1970s mineral survey. It turned out the official study had missed the actual lamproite body by just 50 yards, due to incorrect assumptions about the quartz signatures and lack of visible gold. The sugary quartz they ignored had been the only clue anyone needed. It came down to geometry and a fundamental misread of quartz. During a 1970s state mineral survey focused on industrial potential in the Sierra foothills, geologists conducted soil anomaly sampling over a 100-meter grid. Their aim was to locate heavy mineral concentrations that could hint at base metals, not diamonds. And critically, they filtered their sampling zones to exclude areas with dense quartz veining, assuming those veins signaled past hydrothermal activity tied to gold or tectonic movement, not deep mantle intrusions. This filtering decision altered the entire outcome. One key sample site, flagged as anomalous for chromium and titanium, was rejected from follow-up because the surface was dominated by sugary quartz and lacked visible sulfides or gold color. The assumption was simple: too much quartz meant no value. The field report even included a note: high quartz content may explain false positive, resample elsewhere. But when today's GPS data from the micro-diamond-bearing samples was overlaid on that original grid, a critical pattern emerged. The highest concentration of indicator minerals and verified mantle signal fell directly outside the old grid's boundaries, just 50 yards away from the best sample point. The terrain had been marked unproductive due to quartz saturation and apparent metamorphic overprint. The mistake wasn't just an oversight, it was procedural. Quartz, in their model, was a disqualifier. In reality, it had been the only visible sign of a decomposed lamproite dike now buried under decades of colluvium and weathered serpentinite. The fracture veins, now proven to host accessory ilmenite and pyrope, had been written off as tectonic pressure artifacts. No one broke the samples. No one tested for indicator mineral suites. The opportunity was bypassed, recorded, and archived as a low-priority anomaly. This kind of miscalculation happens more often than most realize. Traditional soil surveys prioritize elements like copper, lead, zinc, and arsenic when chasing ore systems. Kimberlite and lamproite rarely trigger those responses unless deeply eroded. In the absence of visible diamonds or precious metals, sugary quartz is misfiled as noise. Unless a field team is trained in diamond pathfinder logic, or instructed to test indicator suites, entire systems can be missed by a matter of meters. It wasn't just academic. In the Central Valley case, the remap zone revealed a broader cluster of sugary quartz exposures, fracture-aligned across fault structures not previously considered conduits. By revisiting quartz-saturated exclusion zones, the prospector extended his grid another 500 meters and recovered 2 additional heavy suites showing strong ilmenite and chromite concentrations. What the official maps missed, fieldwork and context recovered. The lesson is sharp. Quartz veining, especially sugary and disordered, should trigger testing, not dismissal, when it appears in ultramafic terrain. Survey geometry can fail when the wrong filters are applied. But with field-proven indicators in hand, a new method emerged, mapping not just mineral zones, but repeatable, testable grids based on quartz intrusion behavior. Efficient grid sampling in quartz-heavy terrain requires more than flagging exposures. It demands precision, discipline, and the ability to track indicators back to source. The terrain itself works against you. Sugary quartz appears erratically, fractured by time and tectonics, often strewn across slopes or half-buried in talus. To make sense of it, you need a system that ties every sample to location, depth, and mineral content. Because in the hunt for diamonds, pattern is everything. Start with a 10 by 10 meter grid. This size balances coverage with control, tight enough to catch localized mineral zoning, wide enough to expose drift patterns or migrating indicator suites. Use flag markers or pin flags to create a visual grid over the area of interest, especially where sugary quartz intersects altered ultramafic rock or fracture traces. Each grid cell becomes a discrete sampling unit. From each cell, collect 2 types of material: surface float, loose gravel and quartz fragments, and subsurface fines, taken from 10 to 20 centimeters depth using a trowel or auger. Label all bags with a sample ID code tied to GPS coordinates and grid cell number, e.g., grid B4S for surface, B4D for depth. Consistency in labeling avoids mix-ups and protects provenance. Crucial if lab testing or partner investment is involved later. Each sample should pass through dry sieving before any wet processing. Use at least a number 20 and number 40 mesh stack. Retain both fractions. Coarser material may hold fractured pyrope or ilmenite clumps, while finer sands concentrate chromite and dense metallic grains. Dry screen samples are also easier to store and test incrementally. For on-site heavy fraction work, use a recirculating pan station or water tub with a fine capture system. If using a sluice, opt for vortex or drop riffle matting. Traditional gold riffles are too coarse and often eject smaller indicator minerals. Process each cell's material independently. Never mix concentrates across cells, even if they appear similar. Field testing becomes meaningless if spatial resolution is lost. After washing and concentrating, air dry each fraction and test in this order. Magnet sweep. Dry isolates magnetite, part of the suite, but not diagnostic. Visual inspection under loop. Identify garnet, chromite, ilmenite. Weight in hand plus bounce test. Real chromite/ilmenite feels heavier and settles faster. Specific gravity rig. Optional verify borderline garnet types or unusually dense quartz mimics. Record results on a field log with a simple matrix. Which indicators appear in which cells, in what concentration, e.g., 1 to 5 grains, dense cluster absent. Over time, this builds a heat map, highlighting where the sweet intensifies and where it drops off. That gradient becomes your guide to possible intrusive centerlines or erosion corridors. This structured grid approach also solves a bigger problem: drift. Heavy minerals, especially in older terrain, may have migrated downhill or downslope from source. By tracking their density across the grid, you can often reverse map the likely origin point, even if the lamproite or kimberlite dike is buried or weathered away. A rising curve of indicator density across adjacent grid cells suggests proximity to source. A sharp drop-off may indicate a cutoff or boundary. More importantly, this method is scalable. Whether you're testing a 10 by 10 meter patch or planning a broader 100 by 100 meter survey, the principles stay the same. Isolate, document, repeat. That repeatability is what turns field suspicion into real, testable evidence and prepares the path for confirmatory lab work or investment-grade reporting. But even the best grid can miss what a single, pocket-sized device might catch. Because when the concentrates yield suspect grains, and those grains look too good to ignore, there's one tool that can confirm, on the spot, whether you're holding more than just quartz and indicators. That's where thermal conductivity steps in. Thermal conductivity testing, once confined to gem labs, now fits in your pocket, and it changes everything in the field. With a handheld thermal probe, prospectors can instantly screen suspect quartz-hosted grains that resemble diamond, moissanite, or high-index simulants. It's a game changer, especially when sugary quartz veins in ultramafic terrain start delivering heavy, translucent fragments that don't fit any known mineral logic. If they're real, they'll conduct heat away faster than any quartz ever could. Here's how it works. True diamond has extremely high thermal conductivity, around 5 times greater than copper. When touched with the metal probe of a thermal tester, diamond cools the sensor tip rapidly, triggering a positive read. Quartz, by contrast, is a thermal insulator. Even transparent quartz points, no matter how well formed, will fail the test outright. Moissanite, a common high-index fake, also passes the thermal test, but it conducts electricity too. That's why some field testers now include both heat and electrical conductivity in the same unit, allowing a 1-2 check. Heat test first, then probe for electrical response. Diamond conducts heat, but not electricity. Moissanite does both. These devices are especially powerful when used on washed concentrates. Once your pan yields a few heavy, translucent grains, often colorless, yellowish, or smoky, it's time to dry and isolate them. Test only the cleanest grains, free of dirt or residue. Press the probe tip against a flat or angled face. If the grain registers as diamond on the screen or LED bar, that's a field positive. If it shows conductivity plus electrical response, moissanite is likely. If neither, just quartz, zircon, or glass. In one confirmed case near Reading, a prospector working sugary quartz veins on serpentinized slopes isolated 2 colorless grains from pan concentrates. Under loop, they showed faint octahedral faces, one of diamond's possible crystal habits. Thermal testing in the field flagged both as high conductivity. Electrical testing showed no response. Later lab analysis confirmed one grain as a 0.27 mm natural diamond, rounded and partially resorbed from fluvial transport. The cost barrier for thermal pens has dropped sharply. Some models now retail under $100. While not conclusive proof, they offer strong justification for lab testing, especially when paired with indicator sweet presence. Ilmenite, chromite, pyrope, and the right host terrain. More importantly, they let you test before you waste time or money chasing quartz grains that only mimic clarity and density. But false positives can still slip through, especially in high silica environments where pressure-sintered glass or industrial runoff introduces synthetic debris. That's why thermal testing should always be part of a sequence, not a standalone verdict. Think of it as your final field filter before committing to lab analysis. Yet even thermal confirmation won't help if your garnets mislead you. Many field workers rely too heavily on red garnets as a diamond pathfinder, without realizing that without the right companion minerals, they mean nothing. That's the next trap, and the next correction every serious prospector must make. Red garnets stir the imagination, but in diamond exploration, they're only as valuable as their context. A single deep red garnet grain in sugary quartz may seem like a breakthrough, but without the right mineral partners, it's just a distraction. Pyrope garnet, the one truly linked to diamond stability zones, shares color and density with more common varieties like almandine and spessartine. That's why seasoned field prospectors never trust garnet on site. They verify its company. The first critical rule: pyrope rarely travels alone. In verified diamondiferous systems, pyrope is almost always accompanied by ilmenite and/or chromite, both products of mantle-source magmas like kimberlite or lamproite. Ilmenite, Fatio3, in particular, acts as a red flag for deep earth transport. If you're seeing garnets in sugary quartz zones but can't locate a single magnetic, metallic, or black accessory mineral nearby, you're likely chasing a metamorphic cluster, not a diamond pipe. Fortunately, there's a method to separate real from irrelevant. After isolating garnet grains in your heavy concentrate, pass a strong neodymium magnet over them. Pyrope, being magnesium-rich, may show very slight attraction, but the key is what remains after you remove the magnetics. Ilmenite and chromite should be in that pile. If they're absent, and the garnets appear singly or erratically across the grid, your suite isn't coherent. Next, analyze the garnet shape and luster. Pyrope grains tend to be rounded, glassy, and smooth, often appearing like tiny marbles under 10x magnification. They lack the internal platelets or granular fractures that almandine often displays. The color is typically deep wine red to purplish, occasionally with a subtle orange hue if chromium-rich. But again, appearance isn't enough. That's where specific gravity, SG, testing becomes decisive. Field kits using a scale and water suspension can reveal SG values within plus or minus 0.05 accuracy. Pyrope ranges from 3.7 to 4.2 G/cm superscript 3. Almandine, while overlapping, typically reads slightly lower, between 3.5 and 3.9. If your garnet reads under 3.7 consistently, you're probably holding non-diamond indicators. Still, the strongest test is comparative presence. Take 3 grid cells, one near a sugary quartz intrusion, one downslope, and one control cell 50 meters away. If all 3 yield red garnets, but only the quartz-adjacent cell yields ilmenite or chromite, the source pattern is emerging. If garnets appear across the terrain with no accompanying suite, it's noise. Another mistake: assuming that quantity implies quality. A bucket of red garnets from a schist zone may feel like a win, but in diamond prospecting, one pyrope accompanied by ilmenite and chromite, especially in the right host rock, holds more value than 1,000 almandines. In one field operation near Shasta County, multiple garnet grains were recovered from drainages linked to sugary quartz veins. Initial excitement waned when magnetic separation failed to recover ilmenite. SG tests confirmed the garnets as almandine. But just 30 meters uphill, in a narrower tributary, a smaller sample returned 2 grains of ilmenite, one pyrope garnet with SG 4.0, and a sugary quartz outcrop pinned to altered ultramafic rock. It was the only sample in the area that lined up. Every other find, though more abundant, was irrelevant. This is the real discipline of diamond hunting, knowing when a beautiful find means nothing, and when a sparse, ugly sample means everything. When sugary quartz appears draped over serpentinite, the reaction it triggers depends entirely on who's looking. To most old-school gold prospectors, it's a dead end, a signal of barren ultramafic rock, unlikely to host anything valuable. But to those chasing diamonds, it's one of the most misunderstood and underexplored configurations in the western U.S. Because under the right conditions, quartz on serpentinite isn't a false flag. It's a breadcrumb trail to deep mantle origins. The challenge is knowing how to read the combination. Serpentinite is a metamorphic rock formed by the hydration and alteration of ultramafic rocks, especially peridotite. It's greasy to the touch, typically greenish-black and slick-sided. It forms at subduction zones where mantle material is thrust upward and hydrated. This matters because both kimberlite and lamproite, the two known diamond carriers, travel upward through similar terrain, sometimes using the same ancient faults and conduits.